We're looking at the proportion homework for Chapter 18 with our standard deviation using the formula for the standard deviation of the sample proportions. It's just the square root of PQ over N. And that's really, and then you had the third condition changes where you had NP is greater than or equal to 10 and NQ is greater than or equal to 10. And that's really the only difference between sample means and sample proportions up to this point, right? So when we're looking, you guys, you said 4, right? 4D, is that right? 4C? 4C, okay. 4C. So let's look at chapter 18, number 4, and let's make sure we understand the question here. It says, suppose we have a M&M's bag, so we have 10% of the M&M's are green. Okay, so I'm just going to write some information that I know. Okay, and then it says we buy bigger bags of candy, and these bigger bags have 200 M&Ms each. Okay, so I believe that's N. Okay, we'll see. Again, the students calculate the proportion of green candies they find. So what would P hat be? Well, we don't know, right? And that's the claim is 10%, but we're going to figure it out. So C says, how would this model change if the bags contained more candies? Well, what happens as N increases? The standard deviation gets smaller, okay? And that's really all it's asking you, okay? Because when you were trying to figure out your normal model, you have your P, what is it, 10% are green? 20%? What was the percentage? 10. So 0.10 is the claim, right? Okay. And then you would figure out what your actual proportion was. I don't know. We'll call it P hat. And then go from there. But what we're looking for here is what happens as this increases. Your standard deviation, because in the formula for standard deviation, you're dividing by that number. The more candies you have, the smaller your standard deviation, which means that what? The smaller distance from the mean, which means that this is more likely because it's closer to the mean, right? Okay. The more, basically think about it this way, the more M&Ms you look at, the bigger sample, the more likely your proportion will be closer to the claim, if you think about it that way. Your standard deviation becomes smaller. Okay, that's really all they were asking in problem 4C. Okay. B, you had to just find the number, which was 0.1 times 0.9 divided by 200 and take the square root of it. So you get your new standard deviation of 0.021. Did you get that? 4B, that's the standard deviation, right? Because you have 10% as your P. Yeah. So if you're going to plug that in, square root of 0.1 times 0.9 divided by 200. Okay, and that they got 0.021. And then you had to, it said to use your empirical rule there to describe the proportion might vary from bag to bag. So, well, sure. Standard deviation means that 0.1 is the claim, and then you would just go 1, 2, and 3 above, 1, 2, and 3 below, but you would use this standard deviation. Yeah, you absolutely need to know that. 68, 95, 99.7. Absolutely. You 100% must know those proportions or percentages. Yeah. Is that okay? Okay. You said 9, did I hear that right? That's another one? Number 9. Okay, let's look at that one. 9C. Okay. So in problem number 9, let's look at the context here for a minute. It says, based on past experience, a bank believes that 7% of people who receive loans will not make payments on time. Okay? So that's like your claim, right? 7%. So that's going to be your P. Okay? And then it says the bank has recently approved 200 loans. So what's 200? N. And again, as I'm reading the problem, it's always a good idea to pull that context out and write it down, okay? It says, what are the mean, oh, we're looking at C specifically? Okay, did you get A and B? Okay. Great. All right, so in part C, I think we'll have to do A to get part C anyway, but it says, what's the probability that over 10% of these clients will not make the payments on time? So we're actually given a percentage, right? We want to figure out the probability of that. So we know we're talking about proportions because we are given some percentages, right? So if we want to think about, we have our claim here, and it says over 10%, which is that right? So we're going to put our 0.1, and we're looking at this. Would you agree? Well, in order to be able to figure this out, we do have to have a new mean and a new standard deviation. So we're going to need to check our conditions, right? And our conditions for proportions, let's make sure we can do that. So condition 1 would be randomization. And I don't know that it talks about randomization at all here. It doesn't. So we'd have to say, you know, the sample's not collected randomly. So what would we say? Proceed with caution. All right, our second sample, our second condition is the independence condition, which we often can't check, so we instead use the 10% condition. So we're going to say that 200 is, yes, Mr. Mraz? Well, I'm in the middle of teaching, sweetheart. So 200 is 10%. 200 is 10%. Huh?
Put it in water. You don't want to.
Right. You missed your Valentine yesterday because you skipped class. Whatever. All right. So 200 is 10% of, what do we want to say in this case? All loans by this bank, right? So we'll just say of loans by, does it say the name of the bank or anything? We'll just say by this bank. That's fine. Okay. Boop, boop. Okay, and then the third condition is our new condition. So we're going to say NP is greater than or equal to 10, and NQ is greater than or equal to 10. So we have 200 times 0.07. Is that greater than, what is 7% of 200? 14? So barely, but it is. And then we have 200, and then we have 93% of that. So you should get 186. By the way, these should add up to be the total of n, right? That kind of makes sense. So our conditions are met, which means that I can use my formula for mean and standard deviation. We know that the mean of the sample proportions is just our p, so in that case it's 0.07, which is why I put 0.07 in the middle of my normal curve. And then we can also use the standard deviation. So it's going to be 0.07 times 0.93 divided by 200, and then the square root of that. Let's see what we get here. 0.018, that's what the book got 2. And so once I have my new mean and my new standard deviation, I'm just going to go ahead and look at my sketch. Yeah. So we would say normal CDF. And then we're going to say the lower bound and upper bound, so 0.1, E99. And then our mean of 0.07 and our standard deviation of 0.018. And 0.0448 is what they got. Does that sound right? 0.047, 0.048. And that's your answer. Okay? Okay. All right. How do we feel about this problem? This is a very typical question that you can see on a future quiz or test. Do we know what to do? Okay, so you want to make sure that you're pulling out your information. We have to recognize it's a proportions problem. The percentages dead giveaway that that's what it is. We had to check all of our conditions. We had to find our new mean and standard deviation, and then we just had to draw it and go from there. Better? It's always better when I do it, right? All right, we'll do one more. Daniel? 35C, honey? Okay. All of 35? Let's look at 35. Okay, that'll be the last one we look at. 35, pollution. Okay. So in question 35, the context is about carbon monoxide emissions. And it talks about a car, and it gives you a mean, and it gives you a standard deviation, which means that it's a means, not a proportions problem. Remember that one of the clues is that if you're given a standard deviation, then it's not a proportion problem. Okay, so that's one of your clues there. So in question 35, I'm just going to write down again, read the problem and write down the information that I know. It says that the mean is 2.9, and I'm not going to put the units, but it's grams per mile. And then your standard deviation was 0.4, okay? And it says 80 of those cars, so N is 80. Good. And it says let Y bar represent the mean carbon monoxide level for the company's fleet. That's fine. So Y bar is just really the mean of the means, right? It's just the mean of whatever, which is just 2.9. Okay, and then okay, so A is talking about the model, and remember that we're hoping it's a normal model, right? We hope that it's that. The problem is that we can't verify that until we do what? Check the conditions, okay? So you can't state the model or the parameters of that model until you actually check the three conditions, okay? So we're going to check random, and I don't know that it says random. Another way that we can say this, okay, because we don't, I mean, a lot of times, like think about the problem that we just did with the, what was the context of that one? The banks, the loans, right? So a lot of times we're talking about that bank and they just pick 200 of their loans, right? What's the point of randomization? Well, it's to try to create the most representative sample. Do you agree? So if we can't prove that it was collected randomly, okay? We don't know that it's random. We can say random, not necessarily. Okay, let me write it this way. So we'll say not random, but what will we assume? We will assume that the fleet's 80 cars is representative. And what will it be representative of? Well, all the cars, okay? So that's what we have to think about, okay? So our second condition is that 80 is less than 10% of, well, all cars, right? And it might not be of that particular fleet because it says that their whole fleet's 80 cars. So that would be a census if we're just talking about that fleet. So we're going to assume that that company's fleet of cars is representative of all cars. Okay? Okay. And then our third condition, well, it depends on if we're talking about means or if you have really long legs. Means or proportions, right? And so we're not talking about proportions in this case because we're talking about average carbon monoxide emissions. So we're actually going to be looking at the sample size, and is it large enough? Is 80 bigger than or equal to 30? Yeah, right? So therefore, it's large enough. Okay, so our conditions have been met, which means that I can use my my new standard deviation, right? And that's going to be the standard deviation divided by the square root of the sample size. And my human calculator port of myself says it is 0.045. So if I'm trying to describe the model, this is what you would actually do. Okay, so I'm going to highlight the actual answer. That's the description of the model. Okay, but I do want you to show your work with how I came up with that by checking your conditions and showing the work of the formula. Okay, so all of that really is necessary to answer part A. the capital big N, what does that mean? That means that we're using a normal model. So that describes the shape, right? Because normal distributions are unimodal and symmetric. So we really are talking about shape, center, and spread. So that's why we can describe the model this way. Okay? All right, if we keep going, part B says, what number are we even doing? 35. Okay, sorry. Part B says, estimate the probability that the mean is between 3 and 3.1. Okay? So what we want to do here is put our mean of 2.9. But we actually think it's between 3 and 3.1. So we're actually looking at that. Would you agree? So you're just going to literally do normal CDF, lower bound, upper bound. Oh, wrong one, sorry. It's 3 and 3.1, right? 3 and 3.1, your mean, and then your standard deviation of 0.045. And so they got 0.0131. Good. All right, and then part C says, there is only a 5% chance that the fleet's mean carbon monoxide level is greater than what value? Ooh, I like that question. That's inverse norm. Very good. We're given the percentage, and we have to find the actual value. Now, when we do inverse norm, let's see if we even remember how to do that. And it was, what percentage again? 5%. Okay? So we want to, I'll just draw what they're saying here. So some number, we don't know what it is, but we do know that this percentage is 0.05. Would you agree with that? In terms of a picture of what we're doing here, we're just trying to find that value. So if I was going to type it in, inverse norm, it did say greater than that value, didn't it? Yeah. Okay. So inverse norm, you're going to type in your, not 0.05, 0.95, because if you do 0.05, it's going to give you this low value down here, right? Because it always does the left-hand probabilities, right? So the left-hand probability associated with the value I'm looking for is really 0.95. So inverse norm 0.95. Now if I just did that and that's it, it would give me a z-score, wouldn't it? I don't want a z-score, I want the actual number. So I'm going to put in the mean and the standard deviation. Good. Let's see if that's the right answer. Someone check it. But it looks like it is 2.97. Is that what you get when you type that in? Okay. I like that question. Matter of fact, I like it so much I'm probably going to just make it happen on your next quiz or test. I'm gonna. Totally gonna do it. Kyle, I'm gonna do it. She's watching. Tell JR I said hi. Okay, fine. All right. Anything else? I'm not gonna do a whole nother problem, but better? Catherine? Yeah, okay. Anything else I can help you with the proportions and the formulas, the conditions, what I'm looking for? I really, really, really think it's helpful to draw the pictures, okay? Drawing the normal curve and shading in really clarifies in your brain what you're trying to do and what you're looking for, okay? So I really want to see that step. Matter of fact, I looked for it on the quiz, the partner quiz that y'all took last time. I looked for that, and that was part of the grade. So it's part of the rubric and how I'm looking for it every time. So I want that to happen for you too. Okay? All right. Nothing else? Okay. Let's go ahead then and take out some notes. We're going to do some. We're going to play a little activity towards the end of class today. We're going to estimate a proportion of water on the Earth, which will be kind of interesting. We'll have to Google it. Well, we'll talk about it when we get a little closer. We can estimate. We're gonna do it though. I think it's less than that actually. But we'll find. It's going to fluctuate from day to day depending on how much rain and how much water evaporates. So, I mean, it's going to fluctuate, right? There's no one set answer. We know that. Global warming, all that kind of stuff. The floods I think Florida's going to be swallowed next year. Who knows, right? But we're going to estimate it. All right, but we'll do that in a minute. What'd you say? Oh, you're not talking to me. I don't know. Well, we're going to talk about something called a confidence interval today. And we're going to do it with both means and proportions. So we're really going to, because you can do it for both. I do want you to get your formula sheet out for me because the formula sheet has a very generic formula for confidence intervals. Yeah, someone left one on my desk. Was that you? Okay. I was like, I knew someone left one. Yeah. Uh-huh. So, Hunter, this is one I'll need back, okay? All right. Thank you. But in the very top right of your formula sheet, you'll see something called a confidence interval, and it has a critical value, plus or minus. Do you see what I'm talking about there? Yes. Okay. So that's a very generic confidence interval formula. And we're going to have to kind of put values and numbers and thoughts to each of those pieces. And we'll do that in a minute. But let's just kind of, we already know this. We know the formulas for sample means and sample proportions because we just talked about that really. Okay? Sorry, we've already done this. So we need to think about what a confidence interval really is. Okay? And I want you to kind of read this sentence, and we're going to try to figure out how we can come up with some answers to the question, okay? So 15 years ago, this person, this Dr. Drew, okay, not the Dr. Drew y'all know, but the other Dr. Drew, okay, randomly sampled some sea fans in a reef in Mexico. Okay, and we kind of have talked about oceans are great examples of why we even need inference because we can't find every single sea fan in this case in the ocean to be able to come up with a true mean or a proportion, anything like that. Sea fan is actually a kind of coral, I think. Am I right? Ocean people? Yes, okay. So there's a problem with some of the corals in the world. They're being infected by disease, and those of you who take oceanography, is oceanography a course in the school? Okay. Yeah, y'all are going. Aren't you going on spring break somewhere fun? We are. Oh no, that's not oceanography. That's what Puerto Rico. Yeah. Thanks for inviting me. Appreciate it. And Miss Mackert, thanks. All right. Anyway, a lot of the corals across and major portions of the world are being infected with diseases. You probably have studied things where you have like these algae that come in and infest the water. So anyway, we're trying to figure out what's causing it and how diseased is this type of coral in this particular reef. So they had a uniform depth because they didn't want to think that maybe the depth of the coral had anything to confound the issue, right? We didn't want any other variables in the way, so they just went and sampled in this reef at a specific depth, and they found that out of the 104 sea fans they sampled, 54 of them actually had this disease. So first of all, we need to recognize that this is in fact a proportion problem. Do you recognize that? I don't see percents this time, but what do I see? 54 out of 104. So I do see a proportion, okay? And that actually is the sample proportion. So 54 out of 104, and we can leave it right as a fraction because if you try to change it to a percent, you would have to round. So let's just leave it just like that. Okay, so that's going to be your p hat. Okay? What's the population, oh, I'm sorry, yes. If you can, yes, you can simplify here. So of course we could. So simplify 54 over 104. And it's okay not to, but if you want to, that's perfectly okay. Fine. What is the population proportion? What's the parameter? What's the claim? Nope, that's my sample. That's what I collected. That's the data I gathered. What's the claim? What's the actual percentage of C fans that have the disease? We don't know. Can we ever know? Okay, this is what I'm trying to figure. How can we figure that out? How can I find the true proportion of sea fans in the ocean that have the disease? Well, I can't. It's not possible. Okay, I can't. But what I can do is create an interval that allows us to guess. It's not really guess, but we're going to be a certain percent confident that I really think the true proportion of sea fans that are infected is within this range. It is a very educated guess, okay? And what we're going to do, and this goes back to the formula sheet, okay? If you notice on your formula sheet, it says statistic, plus or minus. Do you see that? Statistic in this case is our sample statistic, the data we gathered. So we're going to take this value, and I'm going to, notice that it says plus or minus right after that? I'm going to add, and I'm going to subtract some number on either side of that to create a range. I think that it's between this and this, where the statistic will be in the middle of that value, of that range. And we think that we can capture the true parameter, because we don't know what it really is, but we think we can get a good range for it. Okay, that's the whole idea of what a confidence interval is. Okay? It's an interval of values, yeah, in which the statistic is the center, and then I'm going to tell you what we're going to add and subtract on either side in a minute. Okay, I think of it's a critical value times something. Do you see that on your it used words, I believe. Do you see that? Okay, so I'm going to put numbers to that so you can see what they are. And it depends on, well, I won't complicate it. All right. Now, we also, in this case, don't know the standard deviation, right? So because we are trying to figure out, well, because it's a proportion, and we have a sample size, and we can check our conditions, we have random, we can go through all of our conditions. We can't find the true standard deviation because I don't know the true population proportion. I'm not given a P, am I? So when we don't have a P, we're going to estimate it. I think I kind of alluded to this in a couple of class periods ago, that we're going to use P hat in our formula for standard deviation. It's no longer called standard deviation anymore when you do that. It's called standard error, okay? So when you can't find the true thing, we're going to have to estimate it, okay? So just kind of keep that in the back of your mind. Because I believe if you look at your formula, it says standard deviation of statistic. Do you see that? Well, we don't know the standard deviation, so we're going to have to use the standard error in this case. Okay? All right. The other thing that I have to explain is what does that critical value thing mean? Okay, so let's talk about it. So here's a question. Can I find an interval in which there's a 95% chance that we'll actually capture the true population proportion? Yes. Okay. 95% is what we call our confidence level. And that 95% is going to come from a normal value, a normal distribution. Because we can go through and check our conditions and know that a normal would apply here. So, if we are 95% confident, okay, we don't know what this is, but we can go 2 standard deviations above and 2 standard deviations below. Would you agree with that? Okay, about 2, right? So 2 standard deviations plus or minus 2. You with me? It's actually 1.97 to be exact, and I'm going to show you how to find the number, but it's approximately 2. You with me? All right. So what did we say here? We said our p hat was 54 out of, what was it? I don't remember. 54 out of 104. Okay, so if I would have 54 out of 104, and then we'd have to find our standard error. Let's do that just real quick, should we? So our standard error, we have to write it as SE. So do that for me real quick. Standard error, tell me what numbers are going to go here, here, and here. Let's find it. Go ahead. Tell me what you get. Can somebody go up there and write the values? Here, Devin, take my pen. Thanks. You can do it on the smartboard itself, hon. Or that. Yeah, I know, but you can just hit this. It's okay. It doesn't matter. Just write. Right? So that's our P hat. And we're getting ready to find our Q hat, which is just not the reciprocal, the complement. Be very careful because don't round it. Okay? You never want to round until the very end, so that's another reason why if you're given it as a fraction, you should probably leave it as 1. Okay? All right. And did you get an answer actually? Okay. Excellent. Okay. So we know, oh really, Ms. Neckert? All right, so it looks to me like 54 divided by 104 is about 0.52. If I'm going to round, just kind of writing the numbers on here. And then I get 0.56 when I added 1 standard deviation and 0.5. Did I write that right? Yeah. And then the other one was 0.6, right? And then over here, if I go backwards, I can say 0.52 minus 0.04, really? 0.52 minus 0.04, and I get 0.48. And I'm going to subtract another 0.04. So we're 95% confident that the true percentage of CFANs that have this disease is somewhere between 0.4, 44%, and 60%. I'm going to say that one more time because every time I ask you to create a confidence interval, I'm going to ask you to interpret it as well. Okay? So the interpretation would be, I am 95% confident. Now 95% correlates according to the empirical rule, 2 standard deviations, approximately. It's actually 1.97, but that's okay. Above and below the mean. So we actually found our new standard deviation, and we added it twice, and we subtracted it twice. We good so far? I'm 95% confident that the actual, either of those 2 words is okay, the true actual proportion of diseased CFANs in what bay was it? Because it's only in that bay, right? In the, reef. The Las, I'm not saying it right, Las Redes, thank you. Las Redes Reef. Is between 0.44 and 0.6. Now you can say 44% and 60% if you want, okay? But that sentence is what we call the interpretation, okay? Now, let's go back to the formula on your formula sheet. Let's figure out what we did, because the formula says it's the statistic plus or minus the critical value times, critical value times, what was the last thing it says? Standard deviation of the statistic. So let's put numbers to this formula. What was our statistic? 0.52, the 54 over 104. Plus or minus. What was our standard deviation of the statistic? Well, we used standard error, but we got it to be 0.04. Now, what the heck is that critical value? Two standard deviations above and below the mean. Okay? We actually call that a z-star value. That's the notation, z-star. Kind of like a z-score, right, with a normal distribution. We're going to call that critical value z-star. And in this case, the z-star that corresponds to 95% is approximately 2. Yes? I just went with what Devin told me it was. It's 0.05 or 0.5? It's about the same. Okay. All right, so it's a bad rounding job. Sorry, Isaiah. Thank you, though, for keeping it real. I appreciate it. You're awesome like that. All right, so I agree. Don't trust Devin. Just kidding. Okay, Mr. Yuck. No, it's okay. I mean, but the process is really what I'm worried about here. Okay, more than anything. Okay, so let's go back to our z-star for a second. Okay, the critical value, we call it our z-star value, and it's very tied to the confidence level that we have. Okay, and we said in our case it was approximately 2 because we know from the empirical rule 95% is 2 standard deviations away from the mean, right? It could. What if I only wanted to be 68% confident? So what would my z-star value be there? 1. What if I wanted to be 99.7% confident? It'd be about 3. Okay? Now, those are approximate values. I'm going to have you find the exact values. Check it. All right, let's go. All right, so let's make sure that we are interpreting correctly. Okay? Can we say, based on our confidence interval, that 51.9% of all C fans are infected? I cannot say that. Because it's just our sample, right? So this, right, and we have no idea. So no, because that's p hat. That's our sample. Okay, we can't say that. We don't know p. We've estimated p. We know it's somewhere between this and this. We can't ever find the actual. We're just going to estimate it. It's probably true that 51. Can we say that? Can we say the second thing? No. How about number 3? We know that the proportion of infected C fans is between this. Do we know that? No. We're 95% confident that that happened, but we don't know it, right? Mr. Yuckface again. Okay? Well, he's tired. I don't know what to tell you. Okay? How about the last one? We are 95% sure that the proportions is between this and this. Yay, that's our happy one. So when I say interpret, if you say any of the top 3 things, what is Ms. Macker going to put on your face? Put on your face. Put on your paper. I'm not going to draw on your face, I promise. A sharper, right on your face. No. I might get in a little trouble for that. No, but seriously. All right. So here is kind of a picture that I tried to draw. No, but there's a meaning by why it's so scattered. Okay, there's a reason. If I took many samples, okay, of CFANs. My first one had 104, my next one was at a different time, and I just collected samples over time. My first sample gave me a range from here to here. That's my first confidence interval. My second confidence interval gave me a range from here to here. They're not going to be exactly the same, are they? Because they're based on your sample, and don't all samples have some kind of variation? So, yes?
What is the red line?
I'm going to tell you in a minute, okay? So, my third sample gives me this, fourth, and so forth. You with me what I'm saying? They're going to vary a little bit. But the red line represents the true population proportion. And are all of the samples going to capture it? Well, here's one that didn't. Do you agree? But 95% of them will. How do we feel about that? Just trying to talk you through about what the interpretation of a confidence interval is. 90 over time, after many samples, 95% of our confidence intervals will capture the true population proportion. I don't know what that is, but we can estimate it to the best of our ability. That is a really heavy concept. And if you can understand and grasp it, and I did my job today, I have to see. It's pretty tough. Okay? But the interpretation is really important, and I will always, always ask you to interpret with a confidence interval. Okay? And so will AP. All right. So let's talk a little bit more before we play our little game. Okay? And let's figure out what this Z star business is. I want to find it exactly. I know it's approximately 2 when I'm talking about 95%, but I want to find exact. How do I do that? Okay? Now, oh, by the way, just so you know, this thing that you add on either side is often called the margin of error. Okay? So you might hear me say those words. You need to write that down. That's pretty important. The critical value times the standard deviation or the standard error of that critical value is called the margin of error. It's what you add or subtract on either side to get your range of values. Okay? So that's called the margin of error. But the piece that's always going to be missing is your critical value. Okay? That's what we have to figure out. Once we find p hat, once we have our sample proportion, can't I find my standard error? We did it before. So those two things go together. It's this critical value that changes. It is tied to the confidence level that we have. Okay? So what we want to do is think about it from this perspective. I already did that. Okay. Let me draw. Oh, ooh, that's pretty. How do I find this number? I told you it was 1.97. It's 1.96. Sorry. Whatever. These values here. Okay? Honestly, I'm going to show you how to find them by hand, but you need to memorize. Often we say 90%, 95%, and 99%. Okay? And those are, it's easy to just memorize the critical values that go with them. 2.576, 1.96, I'm going to have you find that value. But we think about it for a minute, okay? I am, let's do 90% confident, okay? If my middle is 90%, how do I find the Z value that goes with that? Let's think about that for a minute. Let's actually do the 95 first, and then so we have the answer, and I'll show you how we got it. Remember that middle 95%, right? Okay. How much is on either tail? 2.5%. Okay. Do you agree with that? Okay. So how do I find this? How do I find this value? I have the percentage. We did like some homework. How do I find the value? Inverse norm. Inverse norm for what? What percentage am I plugging in? Right, 0.975. Am I going to put in a mean and a standard deviation? I want a Z. It's a Z. So what is the mean? 0. What's the standard deviation? 1. So make sure when you do your inverse norm that you have a mean of 0 and a standard deviation of 1. That's only for z-scores, yes. Okay? So let's see if we can get it. So the inverse norm of 0.975, my default is 0 and 1. And so I get 1.96, don't I? Right? I got it. Yay. So let's find it for the 90%. How do I do that? So let's change what would be different. These percentages would be different, right? So 90 is in the middle now. How much is in either tail? 0.05. So what am I going to be finding? 0.95, right? Because you're always including one of the tails. So the inverse norm of 0.95, 0, 1, is 1.645. That's really the number that we use. Okay. And again, I am okay with, if you don't want to memorize those values, you can find it the same way every time. It's no big deal, because it will always be those values. Okay? So those are the z-star values, always, that are associated with this percent of confidence. Okay? That's how you find it, if you ever forget. No big thing. All right, you ready to throw the ball? I am. Okay, so let's figure out, we already know how to do that. We did it. I want to find the ball. Here we go. Yay. So, let's do this. Let me Google for a minute. Let's actually see. Do you have it? You found it? Oh, you found it. Okay. Well, I want to put it on the smartboard. But tell me what website you went to. Did you Google? Okay, so what, let me type it in, what percentage of the Earth is covered by water? Dun, dun, dun. So, according to Google, and we're all assuming that Google doesn't lie, right, and that it's a good search engine, and this is actually a government website, and I don't know if I trust the Geological Survey or not. They're a little shady sometimes. I'm just kidding. I have no idea. They're fine. But about 71% of the Earth's surface is water covered. That's according to this. All right. Let's try to estimate, because, again, it's an ebb and flow thing, depending on whether it's rained or the polar ice caps are melting. I don't really know. Okay, so let's see. Oh. No, because solid actually is not, well, I bet they go up, right? So like glaciers are tall, so when they melt, they're going to fill up the water, and it would be less land, more water. If you think about it from a proportion standpoint or from a covered standpoint. All right, so here's what you have to do. Everyone has to, on your, let's make it your right thumb, put a small dot on it. Put a small dot on your thumb. Okay? Small enough. I'm going to do it too. It doesn't matter. You can do it on your left thumb if it's easier, if you're right-handed, because I'm having a really hard time drawing a dot with my left hand. But I have a globe. Pretend globe. It's a ball globe. It doesn't matter. Because you're going to catch the ball with two hands. Okay? And we're going to throw the ball around. And as the ball rotates and changes, the way you catch it, you're going to look at where your dot is, and you're going to tell me whether it's land or whether it's water. Okay? Now, this globe was made in China in 2008. So I don't know if I believe it, but we're going to try our best. Okay? Because it's really old. It's what, 17 years old?
2008.
It's all right. I'm glad you love me anyway. 15 minus 8 is not 17.
It's 7.
Yeah.
I'm just saying, you said it was 17 years old.
Because I'm a liar. Anyway, I love you anyway. Love me anyway. All right, are we ready? So every single person has to catch the ball. I'm going to pause the recording while we collect our data. I'm going to make a tally of this up here as you can. All you have to do is look at me and say water, land, and we're going to collect it, okay? I'm going to pause. When you come back on, you'll see the result question. How big enough of a sample do I need to collect in order for it to be accurate? Well, NP has to be greater than, no, not 30. 30 is with means. NP has to be greater than, right? So, no. N times P has to, so P is approximately 70. That's the claim, right? So what's N times 7.7? So we have to be here a while, right? So I'm not sure we can be here for 700 is my point, right? Do you see what I'm trying to get at? 10%, not 10%, 10. You know what I mean. Okay. We're not going to do it to 700 is my point. I just wanted to make sure that you understood that we might be a little off because our sample size might not be large enough. But we're going to be here for a good 10 minutes doing it. So, all right. Sorry, Jasmine. So, obviously, this is an estimate, okay? But it looks to me like, let's count. So we have 5, 10, 15, 20, 25, 30 people did water. 5, 10, 15, 20, 26 did land. Really? Okay. So let's create a 95% confidence interval to estimate the percentage of water on the Earth's surface. Okay, so let's do that. You go ahead and try it. P hat's all you need right now. 30 out of 56. I agree. P hat plus or minus Z star times the standard error of P hat. Isn't that the confidence interval formula? It's your statistic plus or minus your critical value times your standard deviation of the critical value. So P hat you told me was 30 out of 56. Good. Your margin of error we need to find. We want 95% confidence. So what is the Z star that's associated with that? No, exactly. 1.96 exactly. It's approximately 2, I agree. But 1.96, that doesn't change, okay? It only changes if your confidence interval or your confidence level changes.
You want it to be 90 or
95.
I thought that was
Nope. If you actually go back and look, the 95% confident is 1.96, 1.645 is 90, and 2.576. Yes? Yeah, I don't know if they got rid of that yet or not. I think you still do. I think you do. Yeah, I don't use them at all, the Z tables at all. You have to use, yeah, I don't use them at all. For that, yeah. It's actually there. Yeah, and it's different than the one in the book, though. The one in the book gives you the confidence interval value. It actually does. Hang on, let me find it. But it's not something I want you to rely on because I might say, like, find the, to be, these are the most common percentages, but what if I said I find a 62% confidence interval? Like something like 91% confidence interval. And I will do that, by the way. All right, so you need to be able to calculate that number. No, I'm doing it. I'm going there. Hang on, they're right here. Oh yeah, you know what? It's not on here, but it's on the one that AP gives you, I think. One of them, I'll find that for you, Devin, and I'll bring it next class, okay? Does it say confidence interval? Where do you see that? Oh, yeah. That's the two-tail probability table. Yeah, it is this one. But so it's the book that does, but I don't think the AP does, so. All right, anyway. So what's the standard error? You got to figure that out. Um, 2 to 3, never to a single. I mean, use your best judgment here. So about 0.066. Okay. I would really think that 0.067. That's okay. So 0.067 is fine. Okay. So let's find the margin. Oh, do you have a question, Tanner? You're just stretching? Okay. So let's actually, without rounding at all in my calculator, it has the exact value. Let's multiply that by 1.96, and that will give us the margin of error. Okay? So actually, we have 30 divided by 56 plus or minus 0.13. Do you agree with that? So 0.13 is our margin of error. Okay, about 13% margin of error. And we have 30 divided by 56, which is 54%. So we have 0.54 plus or minus 0.13. So let's find, so we'll say 0.54 plus 0.13, and I get 67%. And then if I say 54 minus 0.13, and I get 41%. Okay. Did I capture the claim? What was the claim again? 71. So did I capture it? No. Okay, I'm close, right? I mean, our sample size definitely affected it. Don't you agree? I mean, we'd have to throw around for a lot more. Think about when we threw the ball around, didn't we have like large runs of either land or water for a while? So that makes sense. You'd have to do a big sample size, but we got pretty close. And so that kind of makes sense. But how do you guys feel about this stuff? Do we understand what a real how would I interpret this confidence interval, by the way? Because I always ask you to do that. All right, go ahead, Hunter. You had your hand up. Good. So I'm gonna be real specific. Say your sentence again one more time. So I'm looking for a keyword. That what at this point?
That the true proportion of water on Earth is between 41%.
True proportion, actual percentage of water covering the earth. Make sure you say those words though, okay? I'm not sure if I heard it the first time. Covering the earth. True proportion or actual percentage, either way is okay. Is between 41% and 67%. Okay? According to our itty bitty wee sample with my globe that's probably out of date, but I think we'd be a lot closer. Absolutely. Agreed. Which is why the conditions being checked is so important. Okay? We had to proceed with caution. Good. All right. Now, I am not going to give you a test, a big test, on normal probabilities, binomials, geometrics, and the combining random variables. I just gave you little quizzes on all of that stuff. We are actually starting with the introduction of confidence intervals, the second semester's worth of material. It's called inference. Okay, and we're going to be doing inference from here on out. So you're going to have a test on inference for proportions and a test on inference for means. I think that's how I'm going to break it up this year. I'm not sure, but up to this point we've just had little quizzes. We did have a semester exam that already is on your grade, right? You had your 50-point, your free response part of the exam, right? But we're not going to have another test. And the next test that we have will start with this material. That's what I'm trying to say. Okay? So the binomial, normal, what else did we do? The combining random variables, all that stuff. We're just not going to have a cumulative test on that. I think you're probably okay with it. I would assume you would be. All right, so you guys do have a couple of things to do. You have enough time, I believe, to do your crossword. I have a crossword on the start of inference here. It is on chapters 18 and 19. So if you have your books with you, if you need to borrow one, go for it. Kyle, you can get one when you come back. And then you're going to have a couple of problems to work on from the textbook. And I will look next time for both the one that was due today and the confidence interval homework that's due next time. Counts for 2 different grades, okay? So, oh, sorry, honey. I mean, these don't take that long, right? So I think they'll probably give you like 4 or 5. Okay. Yes, love. Yes. Another pass for me? Oh, you shouldn't have. Oh, Happy New Year. Okay. Nathan, for you, baby. All right, so go ahead and be working on that. Let me pick a few problems from this chapter to look at for confidence intervals, and then we'll go from there. All right, so 11 through 14 are going to be finding your confidence intervals. Make sure you're checking your conditions for proportions, okay, to make sure that they've been met. And then 2, 4, and 6 is just kind of an explanation about the interpreting confidence intervals and that kind of thing. So not too many problems there. So again, next class I'll be looking for this assignment, your crossword puzzle, and then the one that was due today from chapter 18 on proportions. So 3 things due next class. Fair enough?